Hello again. In this video, we will talk about finding expected values using joint, marginal, and conditional probability functions. So we'll talk about how to find the expected value of a function of random variables. We'll then look at some theorems and results related to expected values and do some examples. So let's let g of y1, y2 through yk be a function of either discrete or continuous random variables, say y1, y2, yk, with some joint distribution. Then, in order to find the expected value of this function, we will either sum or integrate, depending on the nature of the random variables, this function g times the joint PDF. Now here, notice something. We are no longer restricting ourselves in our definitions to joint distributions of just two variables. In theory, we can look at joint distributions all the way up through k random variables. Now this can get rather complex, but we can certainly do it. So let's take a look at an example here. Using a familiar PDF, f of y1 and y2 being 2y1, y1 and y2 between 0 and 1, let's find some expected values. Let's find the expected value of the product, y1 and y2, the expected value of y1, expected value of y2, and the variance of y1. So starting with the expected value of the product, y1 and y2. Because this is just simply a function of our random variables, we can find this by integrating our function times the PDF. So we'll take y1 and y2 times the joint PDF, integrated over y1 and y2. Now because the bounds here both go from 0 to 1, this is a fairly straightforward integral to compute. We end up with 1/3 for our expected product of y1 times y2. Now for a single variable y1, for example, we actually have two strategies that we can rely on. Our first strategy is to integrate over the joint distribution. So we could take y1 times the joint of y1 and y2. Or if we know that marginal distribution of y1 alone, we can do a single integral of y1 times the marginal distribution. These are both perfectly valid ways to calculate this expected value. So let's take a look at some theorems or results here. So let's let g of y1 and y2 be a function of random variables y1 and y2. And let c be a constant. The expected value of that constant is still c, so we haven't changed anything there. The expected value of c times the function is c times the expected value of the function. So we can again pull constants to the front of our expected value calculation. Now, if these are additive functions, let's say we have function g1, g2, all the way up through gk, that are simply being added together. So we'd like to find the expected value of g1 plus g2 plus g3 and so on. We can distribute expected values across addition. So we can say that we'll take the expected value of g1 plus the expected value of g2 and so on. So distribution across addition still works. So let's take a look at another example. We have gasoline that will be stocked in a bulk tank once at the beginning of each week and then sold to individual customers. Y1 is the proportion that is available after the tank is stocked. So Y1 is what we have available to sell. Y2 is what we do sell over the week. The joint density function for y1 and y2 is given by the following. We've got 3y1, where 0 is less than or equal to y2, less than or equal to y1, which is less than or equal to 1. Then what the random variable y1 minus y2 represents for us is the proportional amount of gasoline remaining at the end of the week. How much is left over? Let's find the expected value for how much we would have left over. So to find the expected value for how much we would have left over, we've got a couple different strategies here. We could take the double integral of y1 and y2. So we've got y1 minus y2, our function, times the joint PDF. We could go ahead and integrate through this. I'll skip through the steps, and we get 3/8 for that. Because we can distribute, we could also find the expected value of y1, subtract the expected value of y2, and that would also give us the expected value of the additive function. Now, if the random variables are independent, sometimes we can use a shortcut for finding expected values of products. So if y1 and y2 are independent random variables, g is a function of y1, h is a function of y2. These are functions of y1 and y2 alone. Then the expected value of g of y1 times h of y2 is the expected value of g of y1 times h of y2. Most often, these functions will just be the random variables themselves. So something that follows from this is that under independence, the expected value of y1 times y2 is the expected value of y1 itself times the expected value of y2 itself. Again, this is provided that those expectations exist, which they may not. So suppose y1 and y2 have the joint density function 2 times 1 minus y1. Let's find expected value of y1 times y2. We can do this by integrating directly, again, so we can integrate y1 times y2 times the joint density function. If we do that, we get 1 over 6. What we can also do here is use the marginal distributions, find the expectation of y1 alone and y2 alone. So the expectation of y1 alone using that marginal distribution is 1/3. The expected value of y2 alone, again using that marginal distribution, is 1/2. We take the product, we get 1/6. So when we have independence, we have a nice simplifying result for those expected values. That's it for this video. We'll talk a little bit more about joint distributions in the next video. See you then.